Welcome to this short course on machine learning in communications. I am Harpreet Dhillon. I am a faculty member at Virginia Tech, and I'll be the instructor of this course. In this very first lecture, we are covering some machine learning basics, given the diverse backgrounds of the attendees, just to make sure everybody is on the same page. But first and foremost, I would like to thank Professor Adrish Banerjee, my dear friend, Professor Abhishek Gupta, and other faculty members at IIT Kanpur for this very kind invitation. I would have really enjoyed to visit in person, but looks like that will have to wait until the pandemic is over. So let's begin with a bit of a history behind this course. So I developed a course on this topic with my colleague, Professor Mike Buer at Virginia Tech, and we both co-taught that course in fall 2019. So this short course will obviously draw some ideas from that graduate course. So I would like to thank Professor Buer for his contributions, directly or indirectly, that will be appearing in this short course. My graduate student, Mohammed, served as a teaching assistant in that course. So thanks, Mohammed, also for your help. Many of the case studies that I'll be presenting in this course are based on my joint work with graduate students, especially Chiranjeev Saha and Kirtana Boki. So thank you, Chiranjeev and Kirtana, for your great work. Really appreciate. And we are also thankful to the National Science Foundation for supporting our work that has directly or indirectly contributed to the case studies that I'll be presenting. So let's first look at the course modules or my plan for the course. So since there were 4 days, I have divided the course into 4 different modules. So at a high level, my goal is to include both some sort of research results, but at the same time also include maybe around 50%, if not more, of the foundational material as well, right? In the spirit of a summer course. I didn't want to make this just a collection of conference talks, right? So we will be going through some of the foundational results, making background, right? Developing background in this area, and then using those ideas for some research problems as well. So on first day, I will be just introducing some basic ideas, going through some background material. In this lecture, we are covering machine learning basics. In the next lecture, we will be discussing the role of machine learning in communications through some examples, and we'll conclude the day with a detailed case study on this idea of determinantal learning in wireless networks. So my general goal is to demonstrate the role of machine learning for approximating algorithms, right, through this case study. But another interesting connections that we will explore in this case study is the connection of machine learning with another interesting area called stochastic geometry. Okay? So we will go through that at the end of the day today. Module 2 will focus on the estimation theory perspective of machine learning. This will be pretty sort of textbook material, so to speak. So if there are attendees who have had graduate classes on machine learning, you might have come across at least parts of this already, right? But my goal here was to connect popular machine learning algorithms, especially supervised learning algorithms, with what we already know, right? Especially estimation theory. So especially for our younger colleagues, the goal was to show that there is this clear bridge between what they know or what they are learning, right, in grad school with what people use in machine learning. Okay, so in module 2, then we will be covering statistical estimation, and then we will be interpreting popular supervised learnings as estimators of appropriate underlying statistical models. Okay. On day 3, we will start unsupervised learning. I will introduce the general idea of unsupervised learning. Then I will also briefly cover some of the ongoing activities in this area in machine learning called theory-guided machine learning. And we will wrap up that day through a case study on k-means clustering. So this is where I'll be using the unsupervised learning idea on a Grassmann manifold for MIMO codebook design. So this will be a case study focusing on physical layer design. As would be the sort of the theme throughout the 4 days, we will be covering some foundational material and then using those concepts into the case studies, and that will be done on day 3 as well. On day 4, we will continue unsupervised learning. I just really wanted to cover EM algorithm just because it's very useful, very popular. So we'll do that first, and then we will do a case study on distributed learning in wireless networks, which is of particular interest, as we'll see in the next lecture, just because your mobile phones are generating so much data. So this idea of distributed learning or edge learning is particularly relevant for machine learning, the use of machine learning in communication systems. Okay. So let's cover some useful references, right? So when I learned this topic, I found these references particularly helpful. So the first 2 books here are classical books on statistical learning, very popular books on statistical learning. So if you are interested in sort of the probabilistic perspective, right, of learning, then these 2 books would be of interest to you. Third book is a popular book on deep learning, pretty complete book, I would say, on this topic, in case you are interested specifically in the deep learning ideas. Fourth book, titled Understanding Machine Learning from Theory to Algorithms, is a pretty complete book if you are interested in the learning theory, right? So what are the assumptions that we make, right, when we assume that a learning algorithm will work, right? What are the foundational assumptions going into those algorithms? So this is the fourth book. Again, I would say pretty complete. And then I'm also including 2 classical books, Probabilistic Perspective by Murphy and Pattern Recognition and Machine Learning by Bishop, right? So very well-known books on this topic. So I believe the first 4 books at the very least are available on the author's websites. So you can check those out in case you want to go beyond what we'll be covering in this course. All right, so with that brief introduction, right, let's start quickly discussing, so why do we care about this course, right? Why this course? And in order to answer that question, we first need to revisit how we are designing communication systems now, right? And what can be improved using machine learning. So let's look at the conventional design flow for communication systems, which is also called model-based design. And now that we have this complementary data-driven design, right, using machine learning, so we are calling this model-based design for the reason that will be clear now. In this design flow, our step 1 is to acquire domain-specific knowledge, right? Example that I'll give here is the knowledge of the connection of random movement of charged particles with thermal noise, right? We look at this physical process, how is thermal noise being generated, right? That is through this random movement of charged particles. And then step 2 is to use this domain-specific knowledge to develop physics-based mathematical models, right? We abstract that knowledge that we have obtained sometimes from multiple disciplines and come up with a simple to use mathematical model that captures the key sort of essence of that knowledge. And a very popular model, especially relevant for this summer school, is the additive Gaussian white noise channel, AWGN, additive white Gaussian noise channel, AWGN channel. And so this comes from basically central limit theorem, where you have these charged particles, right? Each contributing a small amount to the thermal noise. So your cumulative noise appears Gaussian because of central limit theorem. Then you have step 3 is now to develop algorithms, communication algorithms, ideally with optimality guarantees using the models that we developed in step 2. Okay. All right, so what did we observe from this design flow? So our key observation is that this design flow is driven really by the construction of a mathematical model. Right? You look at sort of any sort of research on communication information theory over the past many decades, right? It starts with a mathematical model that describes the physics of the system that you are interested in studying, right? So then we design the system within the limitations of that model. Okay, so if there is a process that is extremely difficult to describe, right, that is where machine learning could potentially help. So let's look at then the alternate design flow. I always think of this alternate design flow using machine learning as a complementary design flow. Don't think of this as something that will replace the conventional design flow, right? These can likely coexist, as I will make a case as we proceed through this course. Okay. So step one here is to acquire lots and lots of data. Okay. So and we will see what we mean by that. So this is made possible by unprecedented availability of data. Think about the data that is available at the base stations. Think about the data that is available on the mobile phones, right? So there is large amount of data. Step two is now to train a machine learning model, okay? I will explain what we mean by training a machine learning model very carefully in a couple of slides. But for now, just take this as a fact. And this is made possible by unprecedented availability of computational resources, right? So training machine learning models is not easy. You need a lot of computational resources. Partly the reason why machine learning is getting popular now, right, over the last decade or so, even though some of the basic ideas related to, for example, neural networks have been known for decades, right? The bottleneck was always the computational complexity. So now we do have computational resources to do the type of computations needed there. Okay. Now, one can use the trained black box machine, which is what we get when you train a machine learning model to carry out the desired task, right? So what do we mean by desired task? It will be clear from the definition of machine learning, which I'll be introducing very shortly. So there are two key observations. First should be very, very clear, which is the access to data and computational resources is the key, right? As we'll be seeing now in a couple of slides. If we don't have data, then we don't have machine learning. And if you don't have computational resources, then you cannot train the models, right? Second thing, which may not be very clear, especially if you haven't been introduced, sort of exposed to machine learning for communications yet, is the use of domain-specific knowledge, right? How can domain-specific knowledge be used? And it turns out it can actually be embedded in step two, and we'll be covering this in a lot of detail on day 3. Yeah, I'll cover the general idea of this theory-guided ML and also give a very detailed case study where a classical problem in communication theory, right, can help in solving the model-based, the data-based version of that problem using machine learning. Okay. So now let's begin with the definition of machine learning, right? So this is the first thing I wondered actually when I started learning about this step, about this subject. What is machine learning? And thankfully, Tom Mitchell from CMU has provided a very concise definition, which depends on 3 things. Let me first highlight those, and then we'll go through the definition. First part of this definition is experience E. Second part of this definition is task T, right? This is the task that you are training your machine learning model to perform. And then the third thing is performance measure P, which is used to measure how well the machine is doing. And that training happens through this experience E, okay? So a computer program is set to learn. So we say that a computer program is learning. Let me highlight this part, set to learn from experience E with respect to some class of tasks T and performance measure P, if its performance at that task as measured by P improves as it gains more experience E. Okay. What do we mean by this? Can I give one quick example just to make sense of this? Let's take one very basic example from communications. Let's say our task is to decode a BPSK signal at the receiver. Okay, so what do we mean by binary phase shift keying? So you have two possible signals that you are transmitting from the transmitter. One corresponds to bit 1 and the other corresponds to bit 0, right? So think of this as some positive voltage A and minus A, right? Of course, you are modulating and so on, but in the constellation space, this is what you get. You have one point corresponding to bit 1, another point corresponding to bit 0, and the point corresponding to 1 is A, to 0 is say minus A, right? Now, because of noise, what you are actually going to get is not these ideal values, but the values that are somewhere close, because you have Gaussian noise, right? So you might get these type of samples, and every now and then you're going to also have this error where your received signal is far away from its ideal value, right? Similarly, on the other side, you're going to get whenever one is transmitted, these are going to be your received signals. Every now and then you're going to have large errors, right? Now, what this definition is saying is, as you feed this experience, which means as you feed these examples, right? So you label each example, you tell your machine that this is my received signal corresponding to bit 1, this is my received signal corresponding to bit 0, right? Your machine should learn how to decode these bits with a low probability of error. Okay, but of course, classically, we know how to design this receiver. I will revisit this point in the next lecture, but this is what will happen if you want to do this using machine learning. Okay. All right. So after introducing the definition, let's quickly go over the types of machine learning algorithms. Again, just to make sure the terminology is clear to everybody attending the course. So the type of machine learning which is easiest to understand, will be spending some time on this on the first and second day, is supervised learning. So it involves estimating an output, which is called label or response, based on one or more inputs, which are called predictors, features, or attributes. Okay, I'll go through this terminology in more detail through an example. In this case, the supervising outputs are included in the training data. If you remember my BPSK example, right? Whenever I feed my received signal to the machine, I also tell that machine, right, whether that example corresponds to bit 1 or bit 0. That is what we call the supervising output, right? We are telling the machine what is the right answer. So that is supervised learning. In unsupervised learning, right, not surprisingly, we don't have those labels, right? Let's say I just feed that data into the machine without those supervising outputs. And when I came across this for the very first time, right, I thought, okay, how to even pose a problem in unsupervised learning? Just a quick thought process. And the moment you start plotting these data, you immediately start getting ideas. Okay, what do I mean by that? Let me take a very quick example of, say, a vending machine. Let's say you have a vending machine which is separating coins based on, say, mass and size. Okay? So let's say you have your data where you have size here and you have mass here. Okay, so these two, size and mass, are my features. These are predictors, these are attributes, these are inputs. So in this case, I have two inputs. And let's say I have two different types of coins. Okay, so one whose mass and size are small, the other whose mass and size are large, right? Bigger and smaller coin, essentially. So let's say that these are the measurement values that I get when I look at these coins, and I want to train my vending machine to classify between these two coins automatically. Okay, so let's say this was coin one, or the first type of coin. This is coin two. Right, so clearly one can come up with a classifier, right, which will nicely classify these two different categories of coins. And I am giving these supervising outputs, which are labels, meaning each data point here has a label, right, which in this case was a different marker that I'm using. I know that this data point corresponds to coin two, and I know that this data point corresponds to coin one. And on the other hand, let's use a different color here. In unsupervised learning, the difference is I have the same attributes, mass and size, right? But I don't have the supervising output, which means that if I draw the same data, right, I have these data points here and a few data points here. Okay. The difference is that I don't know which data point or which coin this data point corresponds to, which coin this data point corresponds to, and so on, right? I may already know from the domain knowledge that there are two different types of coins, right? That's a different thing. But in just by looking at this data, I don't have those supervising outputs, right? So clearly, if you just think about this data set for a minute, you can see that the clustering type of problems are very natural to pose in this setting, right? I may not be able to attach each of these outputs to a label. What I can tell from this data is that there are two distinct types of points, and in many applications, that is really what we are looking for. Okay. So the type of questions that we ask in supervised learning and unsupervised learning are different, right? So based on whether you have the supervising output or not, we ask different questions. This will be very clear as we move through this course through the fourth day. Now, there is another type of learning algorithm called reinforcement learning. The setting of reinforcement learning is slightly different from the two that we just discussed. It involves agents that take actions to perform a specific task, right? Think of a drone or a robot, right? You might, for a robot, for example, the actions might be to go forward, to go backwards, to turn left, to turn right? And given the environment, there will be a reward associated with each of those actions. And the goal is to construct a strategy that maximizes some notion of that cumulative reward. Okay. It's a very interesting idea, which is useful in communication systems. Even some my students have written a few papers on this as well. The applications of reinforcement learning to communication systems. But because of the limited time, I won't be able to cover this in detail. I will see if we can include maybe one small case study just to expose you to the thought process there. But other than that, we won't be covering any theory behind reinforcement learning in this class. Okay. So after introducing three different types of learning problems, let's look at the essential components of machine learning problem, right? When can I say that my learning problem is meaningful? Okay, is there a way, right, to define what a meaningful learning problem is? And yes, there is at least one possible way through these following three points. First of all, there has to be an underlying pattern. If there is no pattern, there is no learning. It will be clear from one toy example that we'll be covering today. So this is one, of course, key requirement. Second is, it should not be possible to describe that pattern mathematically. The point is, if you can describe that pattern mathematically, you can actually do better. You may be able to come up with optimal solutions. And I will give actually one example in the next lecture from communications, where sure, you can come up with a machine learning algorithm, right? And it will work reasonably well, but you can describe that system almost completely, right, mathematically, and hence applying machine learning to that problem is very futile. Okay? And the third thing is you have to have data to learn that pattern, right? No data, no machine learning. So if, for example, right, we are developing a machine learning algorithm for wireless networks and there is no wireless network data, right, then that task is just not very well defined. Okay. Right. So with this, just basic intuition, now let's look at the sort of design flow of a supervised learning problem, right? Or the supervised learning process. The goal here is, of course, to introduce this process, but at the same time, also introduce some key ideas, key notation that will remain with us throughout the course, okay? So let's look at this very carefully. So in supervised learning, what we have is an unknown target function that is mapping your attributes to the outputs. Okay, so that unknown target function is f here in the first block. But the point is you don't observe that function directly. You observe f through how it acts on the inputs through training examples, right? So these are the type of examples that are given to you. xi is mapped to yi, right? And you have, let's say, n of those training examples, right? And you have to infer something about f from these training examples. Now, these training examples are given as input to the learning model. So let's deconstruct this. What do we mean by a learning model? Okay. So these training examples are given to a learning algorithm A, right? This is the block here, learning algorithm. And another input to this learning algorithm is the hypothesis set cal H. So note here that we are interested in understanding what this unknown target function is. Now, if we search over the space of all functions, that's just hopeless, as we'll see through a very simple toy example. So we have to make some assumptions about, what could this function or general class to which this function will belong. For example, if we know that, looking at your data, that maybe just a linear function will likely work reasonably well, then your hypothesis set could be just a set of all linear functions, right? If you know that maybe a third order polynomial is sufficient, then your hypothesis set will be all polynomials with degrees less than or equal to 3, okay? And as we will see also through an example, it might be tempting to go with a very complex hypothesis class, meaning, okay, why to worry? Well, let's just pick up a hypothesis class with all polynomials with degrees smaller than or equal to 100, right? And we'll see that that's oftentimes not a good idea because of the limited data, right? So I'll try to give that intuition also very briefly as we proceed. Okay. Now, the combination of this learning algorithm and hypothesis class or hypothesis set, by the way, this is also called a model class in case I use that somewhere, right? Model class or hypothesis class, these are all pointing to that set of functions. So I'll be using these terms interchangeably. Now, learning algorithm and hypothesis set is what we term as your learning model. Okay, a lot of attention has been given to learning algorithms, but you have to keep in mind that you are also fixing this hypothesis set. So that is a very important design choice you have to make. And I'll share some insights about that as we proceed along this lecture. Okay, so now after this, your learning model will choose the best candidate function out of the hypothesis set, which will be the estimate of the unknown function. Okay? So note that this is my estimate and it will belong to my hypothesis set. So if your hypothesis set is not carefully chosen, right, then your final hypothesis is going to be faulty. It's just not going to be accurate. Let's take an example These are pictures that I'm using from the ISL book. On the left-hand side, we have, so let me first describe what the experiment is. So this axis here, let's say Z-axis, gives me the income. So this is my output, or this is my label. And there are two attributes or features, right, which determine this income, which are the years of education, which is on this axis, and seniority, which is on this axis, right? And I have a bunch of data points, which are marked by these red markers, right? And here I am also given this exact surface, right? Exact functional form of income as a function of education and seniority. But my machine learning algorithm doesn't know that, right? So what I mean is this blue surface here is unknown to us, right? We are observing that only through training examples, and these training examples are these red data points, okay? So if once I get those data points, I will have to choose my hypothesis class. And let's say that, let's say we look at the data and we decide, you know what, let's just pick up hypothesis class, which is a set of all linear functions, right? And what we do is, so once you make that choice, immediately what you are doing is you are defining your income as some beta 0 plus beta 1 times education plus beta 2 times seniority, right? And here, these beta 0, beta 1, and beta 2 are the model parameters that are being learned using the training data. And this thought process will really remain. Even if you go to neural networks, this is really what you are doing at the end of the day, right? You fix some architecture, there are some model parameters associated to that architecture, and you are learning the values of those parameters through your training process, right? So that's the purpose of giving this example, is to just demonstrate the process. Now, you could ask, you could argue either way. Was this a good enough fit, right? Or is this a good enough model? It really depends. It depends on what you want with this model. If you want inference, which means you wanted to come up with a very simple model to explain how, out of education or seniority, which one matters more to income, I would say this is a reasonable enough model because it sort of captures the overall trend. Now, if you want to do some type of salary predictions, let's say that, and this is actually a key point for you guys to note. Let's say that I pick up this point on my XY space, years of education and seniority, right? And there is no data point which is sort of around that point or test point that I've chosen. So what I would want is, I would want to predict the value, right, of income corresponding to that point. And these prediction problems, of course, the better model we have, better will be the prediction, okay? And in these prediction problems, even if we are not able to infer, right, what exactly is the functional form, that doesn't matter too much to us. And that's why neural networks or these type of non-linear function approximators could be very helpful. It doesn't matter what the functional form is because we are not doing inference. We are just interested in the prediction at the test values, right, which might not have been seen by the model before. Okay. All right. So one other note here, which will be useful for something we will be covering shortly. Note that y, which is y here, is your output, right, may not have a deterministic relationship with x, right? There could be some noise, right, for the lack of a better term, some noise. So this is actually clear from this data set as well. You have a true function, but then your measurements or your examples are a bit noisy around that true function, right? So this is important to note, and something that we will be modeling very shortly, right? This will be included in the statistical interpretation that I'll give very shortly. Okay. So let's quickly establish some notation for supervised learning. So the purpose is to estimate an output, right, label or response based on one or more inputs. That should be clear by now from the example. you have, so we are going to assume that we have D features and we are going to denote the vector of those features by X, right? It of course can be a single element as well if you have a single feature, but we are going to denote these features by X. And the jth value, or the jth element of this vector will be denoted by Xj. All right. And then in our data set, we are going to assume that we have n observations. We have n observations. Remember, we have D, which is the number of predictors that we have, right? N observations means n data points or n examples that are given to you. Okay, so the value of the jth predictor in the ith observation will be denoted by Xij. Right? So this could be, for example, the seniority. This could be the seniority, right, of the ith person in our data set. Right? Now you could write your data set as a matrix, right? So this matrix will be represented by X. So here each row corresponds to one example. Right? So remember, so you have D predictors. So you have X11 corresponding to first person, first predictor, first person, second predictor, and first person, dth predictor, right? And now since we are looking at supervised learning, obviously we have a response variable or an output variable associated with each of these rows. And that's that response variable, right? So there will be response variable corresponding to this row, which is Y1, right, Y2, so on to yn, right? So there is a label. So these attributes are labeled. Okay, so this will be our setting for supervised learning. We can revisit the notation if needed, but I just wanted to make sure that some of the basic things like n samples in our training data and D attributes, right? You just keep these basic things in mind. Okay, so a supervised learning problem can be further categorized as either a regression problem or a classification problem based on the type of the response variable that you have. Okay, so it will be a regression problem if your response variable is continuous, right? For example, if we try to predict the income of a person with a specific seniority and years of education, it is a regression problem, right? Because our output is continuous. Okay? And when your response variable y, right? So in regression, you can say that your response variable y, if it is just a scalar response, it is just some real value, right? In classification, on the other hand, your response variable could be qualitative. Or in other words, it takes values from a discrete set. Let's say y belongs to some set G, right? Think about BPSK example that I gave, right? So each signal was corresponded to the response variable, which was one of the 2 bits, right? So the goal here is to put the observed response in one of the 2 classes in that BPSK example, right? So to summarize, your response variable, if it is continuous, it becomes a regression problem. If it is discrete, it becomes a classification problem. So another key aspect of the whole learning process is the choice of the loss function, right? So you have this true value, right, that you're trying to predict. True value is y, but your estimated or predicted value is y hat, right? Estimated value is y hat. So how do you penalize the error that you are making in your prediction, right? So that error term or loss term or cost term is given by this function L of y hat. Okay, so now the choice of the loss function depends on whether we are doing regression or classification, which is the reason I introduced that briefly in the previous slide. In regression, you could choose a loss function, for example, which is just a squared loss, right? Very popular for the reasons that will be clear very soon. You could just assume that you have a loss function Ly hat, which is just y minus y hat whole square. You can also think about the absolute value loss function. Classification, one loss function that people use is 0-1 loss, where you define a loss of 1 when you make an error and loss of 0 otherwise. It is also common when we look at the cumulative loss, which is also called empirical risk over the whole data set, right? So it is common to assume that your error decomposes over the data set, which means that you can just write your cumulative loss as as this expression here, just the average loss over the whole data set. As we'll see shortly, we will have to be careful with the choice of the loss function as well as how the performance is characterized. And there is also sort of a hidden reason behind why I will be covering the example where I will convey this in something related to communications as well. All right, so I think with this point now, we are ready to cover an important topic, which is model selection. Let me add a page here. I think it will be useful to just draw a couple of pictures. So here, what I'm going to assume is, let's say you have a data set that looks like this. You have Y, you have X, and I'm going to represent my data set, let's say with a black color. Let's say that this is your true function between X and Y. And this is your data set. Through which you are observing this function, right? These are your training examples. So now, you could say, okay, you know what? Let's just use a linear function as we did before. Let's see what we get, right? If you use a linear function, this is what you are going to get, right? And this is what we call model underfitting. Okay, so this purple plot here is underfitting. Now, on the other hand, let's say that we decide that, okay, let's go with a polynomial with a very high degree, right? Let's pick up a hypothesis class which is very, very complex, right? So this polynomial degree of the polynomial, right, which is roughly representing the complexity of the class in this example, let's just put that as Q. Okay, so that becomes Q. So here, this is what I'll get. I'll get, some polynomial which is trying to describe this data as accurately as it can, right? And clearly, this is not ideal because this polynomial, in addition to learning the pattern of the data, is also learning the noise, right? And this is what we call model overfitting, right? And what we need to do is to avoid both over and underfitting. Okay, so how do we do that? So first, recall that our cumulative loss, right, is defined as this average loss. So this will be useful for the discussion. So we are going to define our average loss as E, which is 1 over N. N is the number of examples we have, L of yi, and then I have some yi hat, right? And this is the function value, the estimated function value at some xi, which is my attribute value, right? And then my model parameters are beta, as we saw before in the linear example, right? Beta 1, beta 0, beta 1, beta 2. So I'm just using that as a vector beta. So what we do here is, in order to determine which Q, right, roughly speaking, should we pick, or what should be the complexity of the model class that we pick, we basically divide our data set into 3 parts. We divide this into training data set, validation data set, and test data set. So say, this could be 50%, 50, 60%, and then the rest, validation and test, could be half and half. Again, this is just arbitrary, right? So this could be, say, 20 to 25%, 20 to 25%. Okay, so our step one is to pick up a hypothesis class, which means pick Q, right? And train your model for that Q. So what that is going to give you is beta, right? Basically as a function of Q. So your model is trained for a given value of Q, which is argmin over all possible values of data, right? And you are looking at the training data set. Okay, so you'll get one trained model for each of these hypothesis classes. Now, step two is validation, right? So you can think of Q here as the hyperparameter. This is a term that you might come across if you look at the machine learning literature. So Q is an hyperparameter which is tuned in the validation step, right? So the way we do that is Q star, which is argmin over all Q. So we reuse that model that we trained in the training step, right? And we use that on the validation data set, right? If now your model is either it is underfitting or overfitting, it will not work well on the validation data set. So this is the key step there, right? So then we are looking at this cumulative error over the validation data set. So this becomes train of Q, okay? So here we have now defined, right, or we have determined the model class that we will be using. And step three, likewise, now will be just testing. So just testing a trained model now of which this Q star is also a part, right, on the test data set. So this is what we are looking for now to determine if it is doing what we intend it to do. Okay, so at a high level, what we are interested in is really not the training error, right? You can reduce the training error as much as you want by going into very complicated hypothesis classes, but that's not the goal here, right? The goal is to make sure your learning algorithm works on the new data, or it generalizes, right? So here, generalization error, you can think of that as test error, right? This is a picture from DL book. So as you increase the capacity of your hypothesis class, now think about capacity in terms of the value Q, right? We can discuss capacity in much more formally, but if I do that, I think then I'll probably need to spend a day or so, at least half a day or so, like 1 hour, just on that topic. So we will be not going into that in the interest of time and saving time for the communication aspects as well. But I think for at the level of ideas, just thinking about capacity in terms of Q, which was the polynomial degree for us, is sufficient. So as you increase Q, right, you have more and more polynomials to pick from. So your training error obviously keeps on going down, right? And at one point, your training error, if you don't have too much data, might actually go to 0 because you have a polynomial that completely passes through all the training points, right? But at the same time, your test error, right, it will first decrease to a point and then it will increase, right? So in the underfitting regime, you have error, and then in the overfitting, if you have a model that has learned noise, then it's not, again, not going to work, right? So this shows that we cannot just increase the complexity of the hypothesis class arbitrarily, right? That oftentimes actually is counterproductive. All right, so then the next question we will tackle is, now at this point, we have some background in machine learning, right? We sort of understand what are the sort of the basic aspects of a learning problem. Now, the question I'm going to ask is, why is learning hard, right? And it will result in some of the key assumptions which we make and may not actually be explicitly stated, right, when you look at the learning algorithms more from the algorithmic perspective. Okay, so here is the problem. I have number of features, which is D. Each feature takes a binary value. Let's say Xij. Xij is my jth feature for the ith example, right? Takes a value from this binary set 0, 1, and each response variable is also binary, right? If you don't make any assumptions on the mapping, how many mappings are possible for this setting, right? In other words, what is the size of the hypothesis class that I have? Okay, let's take a look at this very, very quickly. We won't be spending too much time on this. So let's say that we have X1, X2, so on up to XD features, right? Each one of this can take 0, 1 value, 0 or 1. So if you expand this, the number of rows that you are going to get is obviously 2 raised to power D, right? 2 raised to power D rows. Now you also have a response variable Y. And in the mapping, right, each of these vectors, right, this d-dimensional binary vector that you are getting can be mapped to either 0 or 1. Right? So each of these circles can take 0, 1. You have 2 raised to power D rows, which means the total number of mappings that you can get is actually 2 raised to power the number of rows, which is 2 raised to power 2 raised to power D. This is a huge search space, right? This is a huge, huge search space. And even if you are given a large number of samples, let's say you are given n samples, which is very large, still the number of mappings that you haven't observed will be 2 raised to power D minus n. So if D is very large, right? Even large number of examples are not going to help you. Okay. So this is what we get: 2 raised to power D, which is a very large number. Even if you have n examples, that's not going to help, right? So there can be no learning if we don't assume something about the function, right? So one thing that we didn't assume here was that there has to be some type of smoothness in your function, right? If your attributes are close enough, then your response variables cannot be just sampled independently, right? There has to be some correlation in those values, or some coupling in those values, and that is really the underlying assumption that we always make, right, in our learning algorithms. Another way to think about this and think about learning in general is the statistical interpretation. This is something that will be very helpful for us. So here what we assume is that your X, which is your feature vector, your Y, which is the response variable, are sampled from a joint distribution. Okay, X, Y comes from some joint distribution PXY. Okay. And now in order to connect this notion to this function approximation notation that notion that we introduced until now, we can use this simple statistical model for the joint distribution of X and Y, right? So we assume that your response Y is some unknown function f of X, right? Plus some epsilon, where epsilon here is a zero mean error term. It is a random variable zero mean. We are not making any assumptions on epsilon and f at this moment, right? These could be completely arbitrary. To make things tractable for some of the calculations we'll be doing later, we could assume that, or reasonably assume that epsilon is just independent of X. Okay. So we have this model, Y equals to fx plus epsilon. And what this does is, this additive model is actually a useful approximation for the fact that we will likely not have a deterministic relationship between X and Y, right? And that additional noise is what is captured by this epsilon term. Okay. So our objective, right, now under this statistical model is to come up with the estimate Y hat for a given input feature or set of features X, right, which is Y hat is equals to F hat of X. right? So y hat is our estimate, f hat is the estimate of the unknown function that we are observing. Okay. So let's just cover this utility of statistical interpretation. I did have one example to cover. Maybe I'll do that in the very next lecture because it fits in communications as well. Let's cover this utility of the statistical interpretation in this lecture and then conclude. So here we have this setting where x and y, right, are being sampled from a joint distribution pxy. I like to use f of xy for the distribution, but since f is used for the function, we'll be staying with pxy pretty much throughout the course. So now the question I want to ask here is, given x, how do we predict y, right? In other words, we seek a function hx for predicting y given x. Right, and we'll see that once you look at this from a statistical standpoint, you can actually make sense of these questions, fairly rigorously. So let me see if I can add a page and go through this. Again, if you have been exposed to this line of thinking, this is quite straightforward. So this is really for people, right, especially our younger colleagues who are still entering say estimation theory, probability, just to sort of give them this preview that once you start making these type of interpretations, right, things fall in place. So you can come up with very interesting insights. Okay, so as a first step, what I'm going to do is the following. Okay, so I'm going to consider a squared loss function. So I'm going to say that in this in this exercise, I have, right, remember this is my y hat value, right, which is hx. Hx is the function that I desire. So I'm going to assume squared loss, y minus hx whole squared. And the goal is now to determine. I'm defining my goal, which is to determine this function h that minimizes the expected prediction error. Okay, so I'm going to define this expected prediction error as the expectation of the error term, the squared error. And I can talk about expectation here because I'm assuming x and y are sampled from a distribution, obviously, right? Now, using Tower rule, I can write this as expectation over x, expectation over y given x, y minus hx whole squared given x. Okay, so I want now hx that minimizes this quantity. Okay, so it suffices actually in this case to do this minimization pointwise, meaning you fix x equals to some little x, right? The moment I fix x equals to little x, my outside expectation, right, it's not really required because I'm looking at this expression for a given value of x, which means it's only the inner expectation that matters. So what I now need is h of x, which is, I can define my objective now as argmin over c given x equals to x, right? So c clearly here is my function value for that little x that I have already fixed. Okay. Now this expectation, this term here can be written as e of y given x Now this can be easily expanded as e of y given x, y squared given x equals to x, plus you have a constant, so expectation doesn't matter, 2 times minus 2 times c, e of y given x equals to x. Now, right, this is the expression we are minimizing, right? And we want to find the value of c that minimizes this expression. So we take the derivative of this expression with respect to c and equate it equal to 0, right? So dou over, say, dou c equal to 0 of this expression above. This will give us 2 times c minus 2 times expectation of y given x equals to x. This is equals to 0. This implies c, which was just a shorthand notation for hx for me, is nothing but its expectation of y given x equals to x. Now, this is a very interesting insight if you think about it. So what we are saying is, if you are sampling x and y from a joint distribution, right, and your loss is a squared loss, right, the best function that you can come up to predict y, right, for a given value of x is just the conditional expectation of y given x, which is fixed to the value of x that is given to you. Okay. As some of you may already know, this is actually called the regression function as well. And for those of you who have been exposed to machine learning more from the algorithmic side, note that this is exactly what a k nearest neighbor algorithm is doing. Okay. So again, the bigger picture message that I wanted to convey through this very, sort of first order exercise was to show that once you start putting some assumptions, right? And here we actually didn't put something too restrictive. We just said that xy comes from a joint distribution. You can start making sense of why some of the algorithms are developed in the way they are developed. And this will be really the central theme of our second day. Okay, so it looks like I'm a bit out of time in this lecture now. So what I'm going to do is, I had one example planned, so I'll cover that example in my next lecture because it fits within the scope of that as well. So let me summarize this lecture now. We provided a very brief introduction to the basics of machine learning. Right, the goal was to make sure, given the diverse backgrounds that we have in this course, the goal was to make sure everybody is at the same page, right? If we discuss, for example, hypothesis class, you should now sort of know, at least you have some intuition of what it is, right? We also defined machine learning, introduced types of ML algorithms. We introduced supervised learning, both from the statistical and function approximation viewpoints. We sort of connected them. We also discussed model selection very briefly, right? And this was just to make sure that, especially if you haven't been exposed to machine learning yet, you might be tempted to think, oh, why aren't we going with a very complex model class and be just done with it, right? But that's not always the right thing to do. All right. So in the next lecture, I will be covering or going over rather the role of machine learning in communications. All right. Thank you so much for your attention.